Hi guys, welcome back to my channel. This is Dr. Rajeshwar from YR PharmaTube. In the previous video, we learnt the aromatic and aliphatic hydroxylation reactions. If you did not watch the video, hit the I button on top right of this video to watch it. In this lecture, we shall try to understand the other types of oxidation reactions such as epoxidation, oxidation of benzylic carbon atoms, oxidation at allylic carbon atoms, and oxidation at carbon atoms alpha to the carbonyl and imine groups. At the end of this lecture, you should be able to understand the four different types of oxidation reactions like epoxidation, oxidation of benzylic carbon atoms, oxidation at allylic carbon atoms, and oxidation at carbon atoms alpha to the carbonyl and imine groups. All these reactions are catalyzed by cytochrome P450 enzyme in liver. Coming to epoxidation or oxidation of alkenes or olefins or oxidation of aliphatic pi bonds. Cytochrome P450 enzymes normally oxidize double bonds to the corresponding epoxides. Epoxidation is an oxidation reaction in which an oxygen atom is added to an alkene. Drugs possessing carbon-carbon double bonds are oxidized to 1,2-diols through the formation of epoxides as shown in the figure. Thus, the metabolic oxidation of olefinic double bonds leads to the corresponding epoxide. Hence, the reaction is called the epoxidation. The epoxides produced in these reactions are also known as arene oxides or oxiranes. Thus, epoxidation is a chemical reaction where an oxygen atom is joined to an unsaturated carbon to form a cyclic three-membered ether. The epoxide metabolites are more stable than arene oxide metabolites formed from aromatic compounds. Epoxide metabolites also undergo enzymatic hydration by epoxide hydrases into trans 1,2-dihydrodiols or 1,2-diols. In addition to the enzymatic hydration, epoxides undergo conjugation reaction with glutathione. Epoxides are normally unstable intermediates but may be stable enough to be isolated from polycyclic compounds, that is, the pre-carcinogenic polycyclic hydrocarbons. They vary in their stability, which depends on the electron density of the double bond being oxidized. It is to note that the higher the density, the more stable the epoxide. It has been suggested that epoxide formation is the first step in aromatic hydroxylation. For example, benzopyrene upon epoxidation is converted into its 4,5 epoxide. As discussed above, epoxides are substrates of epoxide hydrolase forming dihydrodiols, but they may also spontaneously decompose to form hydroxylated products or quinones. For example, the anticonvulsant carbamazepine undergoes olefinic oxidation and yields a number of epoxides, and the 1011 derivative is stable enough to be pharmacologically active. While bromobenzene 3,4 epoxides half-life in blood is less than 14 seconds. Generally, arene oxides form phenols or diols in the presence of water, as does carbamazepine 1011 epoxide, although the cytosolic enzyme epoxide hydrolase is present to accelerate this process. Isolation of glutathione or mercapturic acid metabolites in a biological system provides indirect evidence for the formation of epoxides. For example, styrene in rats produces two isomeric mercapturic acid metabolites resulting from nucleophilic attack of glutathione on styrene epoxide. Aflatoxin B1 is a naturally occurring hepatocarcinogenic agent. It contains an olefinic double bond between C2 and C3 adjacent to cyclic ether oxygen. This olefinic double bond undergoes epoxidation to give highly reactive and toxic 2,3-epoxide metabolite. The cellular toxicity associated with some olefinic compounds can be attributed to their highly reactive epoxide metabolites. Certain groups of olefinic compounds irreversibly damage the cytochrome P450 enzyme system. This is due to the covalent binding of corresponding epoxides to the heme portion of the enzyme. For example, long-term administration of allyl isopropyl acetamide, secobarbital, and fluoroxine leads to inhibition of oxidation metabolism, undesired drug interactions, and prolonged pharmacological effects. Here, in this example, alkofenac, an anti-inflammatory agent, is oxidized to dihydroxyalkofenac via epoxide. Other drugs shown here which undergo olefinic oxidation or epoxidation are protriptyline, an antipsychotic drug, and cyproheptadine, a H1 antihistaminic agent. The next reaction is the oxidation of benzylic carbon atoms. Carbon atoms directly attached to aromatic rings are called benzylic carbons. These benzylic carbons undergo oxidation, forming the corresponding alcohol or carbonyl metabolite. Primary alcohol metabolites are often oxidized further to aldehydes and carboxylic acids. Secondary alcohols are converted to ketones by soluble alcohol and aldehyde dehydrogenase enzyme. Alternatively, the alcohol may be conjugated directly with glucuronic acid. For example, tolbutamide is oxidized to the corresponding alcohol and carboxylic acid. Both alcohol and carboxylic acid metabolites have been isolated from human urine. Similarly, the benzylic methyl group in the anti-inflammatory agent tolmetin undergoes oxidation to yield the dicarboxylic acid product as the major product metabolite in humans. The selective cyclooxygenase 2, that is COX-2 anti-inflammatory agent celecoxib, undergoes benzylic oxidation at its C5 methyl group to give hydroxycelecoxib as a major metabolite. Significant benzylic hydroxylation occurs in the metabolism of the beta-adrenergic blocker metoprolol to yield alpha-hydroxymetoprolol. Additional examples of drugs and xenobiotics undergoing benzylic oxidation are given here. Moving on to oxidation at allylic carbon atoms. Oxidative drug metabolism is also commonly observed in microsomal oxidation or hydroxylation at allylic carbon atoms. Allylic carbon atoms are shown in the allylic group in the figure. For example, delta-1 tetrahydrocannabinol, abbreviated as delta-1-THC, the psychoactive component of marijuana. This compound contains 3 allylic carbon centers at C3, C6, and C7. Allylic hydroxylation occurs extensively at C7 to yield 7-hydroxy delta-1-THC as the major plasma metabolite in humans. Pharmacological studies show that this 7-hydroxy metabolite is as active as or even more active than delta-1-THC by itself and may contribute significantly to the overall central nervous system's psychomimetic effects of the parent drug. Hydroxylation also occurs to a minor extent at the allylic C6 position to give both the epimeric 6-alpha and 6-beta hydroxy metabolites. Metabolism does not occur at C3, presumably because of steric hindrance. In the second example, the sedative hypnotic hexobarbital undergoes allylic oxidation to form 3-hydroxylated metabolite which is susceptible to glucuronide conjugation as well as further oxidation to the 3-oxo compound. Hexobarbital is a chiral barbiturate derivative that exists in 2 enantiomeric forms. Studies in humans indicate that the pharmacologically less active R- enantiomer is metabolized more rapidly than its S plus isomer. In the third example, pentazocine undergoes allylic hydroxylation at the two terminal methyl groups of its N-butynyl side chain to yield either the cis or trans alcohol metabolites shown in the diagram. In humans, more of the trans alcohol is formed. For the hepatocarcinogenic agent safrole, allylic hydroxylation is involved in a bioactivation pathway leading to the formation of chemically reactive metabolites. This process involves initial hydroxylation at the C1 carbon of safrole, which is both allylic and benzylic. The hydroxylated metabolite then undergoes further conjugation to form a sulfate ester. This chemically reactive ester intermediate presumably undergoes nucleophilic displacement reactions with DNA or RNA in vitro to form covalently bound adducts. As shown in the scheme, nucleophilic attack by DNA, RNA, or other nucleophiles is facilitated by a good leaving group, for example sulfates, at the C1 position. The leaving group tendency of the alcoholic hydroxyl group itself is not enough to facilitate displacement reactions. Importantly, allylic hydroxylation generally does not lead to the generation of reactive intermediates. Its involvement in the biotoxification of safrole appears to be an exception. The last reaction of the lecture is the oxidation at carbon atoms alpha-2 carbonyl groups and imine groups. The mixed function oxidase system also oxidizes carbon atoms adjacent, that is alpha to the carbonyls and immunofunctionalities. An important class of drugs undergoing this type of oxidation is the benzodiazepines. Benzodiazepines such as diazepam, flurazepam, and nimetazepam are oxidized to their corresponding 3-hydroxy metabolites. The C3 carbon atom undergoing hydroxylation is alpha to both a lactam carbonyl and an immunofunctionality. For diazepam, the hydroxylation reaction proceeds with remarkable stereoselectivity to form primarily 90% of 3-hydroxy diazepam, which is also called N-methyl oxazepam, with the S absolute configuration at C3. Further, N-demethylation of the later metabolite, that is N-methyl oxazepam, gives rise to the pharmacologically active 3S plus oxazepam. Hydroxylation of the carbon atom alpha-2 carbonyl functionalities generally occurs only to a limited extent in the drug metabolism. An illustrative example involves the hydroxylation of the sedative hypnotic glutathione to 4-hydroxyglutathione. This is the list of references followed for the lecture. That's all in this video. The epoxidation, oxidation of benzylic carbon atoms, oxidation at allylic carbon atoms, and oxidation at carbon atoms alpha to the carbonyl and imine groups. In the next lecture, we will discuss about the other oxidation reactions catalyzed by cytochrome P450. Till then, never stop learning and never stop watching my videos. Thank you for watching this video.